Hi, welcome back. In this lecture, I want to talk about a useful and insightful representation of a qubit called the Bloch sphere. Before talking about how to represent in a geometrical form the qubit, we can think about how to represent geometrically complex number with modulus 1 or amplitude equal to 1. So for a given complex number C with the real part x and imaginary part y, whose modulus is 1, so the amplitude is 1, there is very nice intuitive way to represent using a circle. So we can represent our number, the complex number, as an arrow of length 1 from the origin of the circle of radius 1. So that's the circle that has amplitude 1, and then we can use a vector with that forms an angle with the origin. So the important part is that every complex number of radius 1 can be identified by an angle phi that the vector makes with the positive x-axis. We just need this number here that is phi. So there is an analogous representation of a qubit as an arrow from the origin to a three-dimensional sphere. This representation is called a Bloch sphere. A generic qubit is in the form of psi, so we have our state psi that can be represented as a superposition of the basic state 0 and 1, and then as we saw before we have these complex number that are normalized, so they are the sum of the square modules of these two coefficients is equal to 1. So if you think about, we need two complex number so that I have the real and imaginary part. So there are for representing our state psi, it looks like that we need four real numbers. So the real and imaginary part for two complex numbers. So these are four real numbers, and these are involving the qubit. In reality, it turns out that there are only two actual degrees of freedom to the three-dimensional sphere. So technically, as you can see here on this Bloch sphere, we will go in detail a little bit later, but we need just an angle phi and theta and 5. So we will need only two actual degree of freedom instead of 4. So let's look at why we need 2 instead of 3. Well, if you're using a polar description of our C0 and C1, we can express our state psi using this formulation here. There are still 4 parameters, rho naught, ry, and then we use phi naught and phi 1. However, we can kill the phase by basically manipulating this expression here, and we can do the so-called killing of this phase. So we can just represent the phase as a difference of phase. So in this case, we have only 3 real parameters, namely the 2 amplitude, and then we combine the 2 phases in one that is just the difference of the 2 phases. So this is equivalent. Also, to kill the third parameter, the third degree of freedom, we can actually use this normalization constant. So we know that our vector is can just be in a sphere or radius 1. So we can use this additional transformation, express rho naught and r1 depending on an angle theta. Because this normalization equation holds, we can use this expression. By plugging in the original expression, we can see that our quantum state psi can be expressed using the basic state 0 and 1, and then we use only 2 parameters, so theta, that is the angle that we just introduced, and then 5, the angle that we introduce as just the difference of the 2 phases. So as only 2 real numbers are necessary to identify a qubit, we can map our qubit to an arrow from the origin, that is here, to the three-dimensional sphere of radius 1. And this is called the Bloch sphere. So we can represent any quantum state psi as an arrow that is going from 0, the origin of our sphere, to radius 1 here, and then we just need 2 angles as I said before, the angle theta and the angle phi. So it's very important and that we can represent every qubit by just using two angles. The two angles will take the name of a latitude for theta. So this angle here is the latitude, and then we have the longitude on this plane. This is very similar on how we describe a point on the Earth. We always provide the longitude and the latitude. An important part to note on the Bloch sphere is that the North Pole in this case correspond to the state 0. This means that if we have our quantum state is the state 0, this will be this arrow here, and in case of state 1 it will be just an arrow in the opposite direction. So what is the physical meaning of the Bloch sphere? Well, we know from the previous lecture that phi is the angle that psi makes from the x along the equator, right? So this is phi, and then we have a theta that is half the angle that psi makes with the z-axis, right? So this is the angle here. So when a qubit is measured using the standard basis, that is the basic state 0 and 1, it collapses to a bit. So when we do a measurement, is either up here to the north, so state 0, or an arrow that is going in the opposite direction, that is 1. An interesting point is that the probability of which pole the qubit will collapse to, so when we do the measurement, it will collapse either to 0 or to 1. It depends exclusively on how high or low the qubit is pointing. That is the latitude. So for instance, you see here that we have this psi, and how close is to the state will basically determine how likely is to measure this state in a state 0 or in y. So if we have, for instance, a vector, our qubit is represented on the Bloch sphere in this way. It turns out that at the qubits then there is a 50-50% to collapse either to 0 or to the 1 state. So any vector on the equator has the same probability to collapse to 0 or to 1. So the probability of measuring 1 or 0 is the same. As you can see, it's quite interesting to visualize using graphical representation also the probability. So we know that is normalized, so we need to move on this sphere, and then how close to 0 and how close to 1, it will tell us how likely is to do the measurement to a basic state. Finally, an important part is that the Bloch sphere also to allow us to represent any transformation on the qubit. So any transformation on a qubit in quantum computing is represented by a unitary matrix that is preserving a norm. So the norm of our vector will be the same. The Bloch sphere is interesting in that every unitary 2x2 matrix, so that is a gate working on one qubit operation, can actually be visualized as a way of manipulating a vector on the Bloch sphere. It turns out that everything unitary matrix is isometry. That means that preserve the norm of the vector. This means that such a matrix maps qubits to qubits, and the inner product is preserved. Any quantum operation on a qubit is corresponding to a rotation or inversion of the Bloch sphere. This is the last slides of this lecture, and talk to you soon.